Hello students, in this session we are going to study the cantilever beam with point load. Right, and what we want to find out? The deflection and slope for a cantilever beam with point load using double integration method, right? So we have to find out, basically to find the slope and deflection of this beam using double integration method. I am writing in short, DIM means double integration method. So using double integration method, we want to find out the slope and deflection of a cantilever beam where there is a point load at the free end, right? Now we know the equation, deflection equation. This is our deflection equation. EI d2i by dx square is equal to minus m. It means bending moment is required. So if this is a beam A to B, the bending moment will be valid between A to B because there is only one load. So if we take a section here at a distance x, from the free end, suppose at a distance x from the free end, if I take the section and find out the bending moment here, what will be the bending moment here? That is mx. That will be equal to w multiplied by the distance, right? And it will be negative because it is a hogging bending moment. So this is minus wx. And this bending moment can be put here in this equation, put in 1, and we will be able to solve this problem and by integrating this, right? So we will get EI d2y by dx square will be equal to minus and minus will become plus, so this will be wx, right? Integrate it once and we will get the slope, right? So after integrate and we will get the slope EI dy by dx. EI dy by dx will be equal to the integration of this, that is wx square by 2 plus some constant c1. So this is the slope EI dy by dx. Dy by dx here is the slope, right? But c1 is unknown. How to find out c1? The unknown c1. We will use the boundary condition here. What are the boundary conditions? What are the boundary conditions for a cantilever beam? We have already discussed that at x is equal to L, suppose the length of this beam is L. So at x is equal to L, dy by dx will be equal to 0. Slope is 0 at fixed end. The slope is 0. You know there that this is the deformation and the slope at this point is 0. And also at x is equal to L, y is 0. There is no deflection in the beam. So we can put this first boundary condition, that at x equal to L, dy by dx will be equal to 0. Put here, you will get c1 as this is 0, so it will come out to be minus wl square by 2. So this is the value of c1. This is the value of c1 minus wl square by 2, right? Put here again and we will get the equation of slope. So EI dy by dx, EI dy by dx will be equal to wx square by 2 minus wl square by 2. So what is slope then? Slope theta or dy by dx will be equal to, divide by EI, you will get wx square by 2 EI minus wl square by 2 EI. So this is the slope which is valid from A to B, from B to A. It is valid from B to A. So this is the slope which is valid from B to A because there is no other load in between, right? So it is valid from B to A. So this is the slope of this beam, right? But as I said that our aim is to find out the maximum slope, and the maximum slope is at x is equal to 0 because at this point the slope is maximum. We know that at this point theta b, the slope is maximum at theta b. So theta max will be at x is equal to 0. So theta max or theta b will be at x equal to 0. Put here x is equal to 0 and you will get the slope. So theta max you will get as Put here x is equal to 0, so this will be minus w L square upon 2 EI. Minus w L square upon 2 EI. This is the maximum deflection or maximum slope. Right? Now, maximum slope. This is not maximum deflection, this is maximum slope. Right? So, once again integrate this equation, and you will get the deflection. So integrating this equation, this was the intermediate equation which we have received after the putting the value of C1, right? If this is equation number 1, this is equation number 2. So integrating equation number 2 again. So integrate equation number 2 again, you will get the slope deflection. So this will be EI multiplied by y, because dy by dx will become y, that will be equal to wx cube by 6. So that will be equal to wx cube by 6 minus wl square by 2x minus wl square by 2x 2 multiplied by x. Right, integrating this and integrating this, and then there is another constant, suppose C2, and again boundary condition we can apply that at x equal to L, y will be equal to 0. Put here, you will get the value of C2. So solving it, you will get the value of C2 as, solve it and get the value of C2 as WL cube by 3. Solve it, you will get WL cube by 3. So this is the value of C2. Put the value of C2 here and you will be getting the slope. So finally, I am writing the final result that y will be equal to wx cube by 6 EI, wx cube by 6 EI minus WL square by 2 EI multiplied by x, and this plus WL cube by 3 EI. So this is the deflection of the beam which is valid between B to A. Wx cube upon 6 EI minus WL square by 2 EI into x plus WL cube by 3 EI, right? So this is the deflection of the beam, this is the answer, and this is the answer, right? This is the answer, and this is the maximum slope and maximum deflection, and maximum deflection will be at x is equal to 0. This is the y max. This is y max at x is equal to 0. At x is equal to 0 at B point, right? So for y max will be at x equal to 0. Put here x is equal to 0, you will get the maximum deflection. So y max will be equal to WL cube by 3 EI. So this is the maximum deflection, right? So this we want to solve, maximum deflection and maximum slope. So maximum slope is WL square upon 2 EI, maximum deflection is WL cube by 3 EI. So this is how we obtain the slope and deflection for a cantilever beam which is loaded by point load at the free end.